that one is.
Well, okay, if we've got these two mixed anhydrides, we went too far, right? If we've got these two mixed anhydrides, what would make this one slightly higher energy than this one?
Got an asterisk.
More charge density?
The negative charge density here is enough to affect the energy of the overall molecule. Question, Kyle? You're thinking awfully hard over there.
What makes the acetophosphate the same energy as the phosphocreatine?
Well, but we haven't gotten to phosphocreatine yet, so let's consider the phosphocreatine. Okay, the phosphocreatine, or creatine phosphate, or creatinine, I've heard it called. Creatinine. And you get muscle heads using stuff, and it gets butchered. Okay, creatine phosphate, phosphocreatine. What's that for? What does phosphocreatine do? It stores what?
It's something your muscles use it, right?
Your muscles use it. And so, there is an enzyme, creatine kinase.
Aren't there like wrestlers that have died from taking this or
Oh
something?
yeah, okay. People do all kinds of dumb stuff. So, right, creatine kinase takes creatine plus ATP, and in an equilibrium reaction makes creatine phosphate plus ADP, right? That's an equilibrium. And given that it says, right, if we're ATP, ADP, that would be using this reaction, right? So phosphocreatine is a little higher energy. So this equilibrium lies a little farther toward that react side than that side, right? Looking at the relative delta G's. Do we agree with that? Okay, and we're happy with that. Okay, so what is creatine for? Where do we find it mostly? Muscle, right? So it is synthesized in the muscle.
Doesn't it prevent like lactic acid buildup or something? Like makes you less sore or something?
No?
So when you burn all your ATP.
Yeah. The creatine in the muscle is there as a phosphate store. So, right, here we are. You are a muscle, right? You would like to work beyond the amount of ATP that you have immediately stored. So at rest, your mitochondria make a lot of ATP. And so what happens to this equilibrium when you are at rest? If you make a lot of ATP.
You go to the right.
Right? You remember, this ATP is coming from mitochondrial action, so you build this up, and so the equilibrium gets pushed that way. So you make a lot of phosphocreatine, which makes ADP, but since you're at rest, what does your mitochondria do with that ADP? Makes it back into ATP and keeps pushing the equilibrium that way. No, it's not. Because right, what it's doing is storing a lot of phosphate as phosphocreatine. Because, if we look at the structure, right, we go to phosphocreatine. Phosphocreatine only has one phosphate group, right? While ATP has a triphosphate group. The problem is the more negative charges you put on one place, the more that molecule becomes attractive to divalent cations. Now, what is the predominant divalent cation that we worry about?
Calcium?
Calcium. So one of the reasons why we want to keep calcium concentrations low in the cytoplasm is that calcium tends to try to precipitate with these phosphate compounds. Calcium phosphates have very low solubilities. And so A monophosphate interacts with calcium less strongly than a pyrophosphate or a triphosphate. So we need ATP equivalents in the cell, but if we try to put too much ATP in one place, it causes trouble. So what this lets us do is create a more soluble pool of high energy phosphates that we can load up in the cell. So, mitochondrion makes ATP, pushes it that way. Mitochondrion takes the ADP, makes more ATP out of it, pushes this even farther that way. Okay, so now, once we reach the end of rest, so at rest, what's the free creatine concentration going to be?
No.
Big or little? Little, yeah. So we got a very, very low concentration of that. What's the ATP amount going to be? High. Right? Most of our ATP, ADP is going to be in the form of ATP. What's our creatine phosphate? High. What's our ADP concentration going to be? Low. Right? Okay, so at rest. So, now we have to make a sudden aerobic effort. No, I'm sorry. Anaerobic effort. You have to make a sudden anaerobic effort. What's going to happen?
ATP is going to.
We're going to suddenly use up a bunch of our ATP. But ATP in the cell is limited. So we're pre-equilibrium, suddenly this gets low. This is still low. This is still high. But because we've made this sudden effort, this suddenly becomes a higher concentration. Are we still at equilibrium? No. So when we allow it to equilibrate, what's going to happen?
Medium.
That's going to cause flow in that direction. And so our creatine concentration goes up, but our ATP concentration goes up as well as these drop. And now we have more ATP that we can use for activity. And this process is faster than glycolysis. So this lets the muscle, in a time frame shorter than glycolysis can respond, replace suddenly used ATP and bridge that little time gap that it takes between intense, short burst effort and the reaction that we get from glycolysis to replace that ATP. Does that make sense? So, that's what the creatine is for. And so that's why people doing high intensity activity want to try to boost their creatine. If you can increase the concentration of creatine in cells, then at rest you can increase the amount of creatine phosphate that you make, which gives you a little longer burst of creating this ATP in that high intensity exercise, right? That's the theory that people are working on. What's the problem with that idea on its surface?
You're attracting the calcium, right? Like you said that if you have like phosphocreatine, then you're attracting the divalent Calcium?
Now remember, phosphocreatine attracts them less strongly than ATP
Oh,
does.
okay.
That's part of the point
Better
of
than
using it.
ATP.
It lets
Okay.
us create this pool of more soluble high-energy phosphate molecules that can be turned back into ATP energy when we need them.
We have less ATP to use to begin with because you'll.
That, listen,
Forcing reaction this way.
but we want to force the reaction that way. Let's think more globally. Where do we want this to work? In the muscles. How are we going to get it in there?
What was?
Yeah. Okay, but okay. Now, how are we going to get it in there? How do things get into cells?
Transport it.
Hmm? Well, we can transport it in the bloodstream, but let's go back to our membrane transport. Right? What are the ways we can get things in there? There's simple diffusion across the phospholipid bilayer. Even if we take the phosphate off, if you just take creatine, right? Creatine, you got 3 nitrogens and a carboxyl group. Is that the kind of molecule that will diffuse across a membrane bilayer? Why not?
Yeah.
What? Too much charge, too polar, right? Only those things that have the nice balance of polar and nonpolar will effectively diffuse across a biological membrane. So we can't get it in that way. So if we can't get it in that way, what do we need? We need some kind of transporter, either a facilitated diffusion carrier or an active transporter. What do we not have for creatine? Either one of those, right? Because the muscle cell counts on its own synthesis of this, right? The muscle cell makes this itself. It doesn't import it from other places. So, Robbie was talking about injecting. Now, you could say, well, okay, it may not get into the bloodstream, but what about an intramuscular injection? Well, that would be great, except you would have to inject every muscle. And oh, by the way, you're still sticking it in between the cells and so you're still just creating a big bubble of this stuff around the cells. You're not getting it into the cells. So you'd have to inject every cell of every muscle that was going to do the high intensity activity that you wanted this to work on. Yeah, does anything about that sound scientifically valid? So, people take it because, there's creatine in muscles, right? So people fall for this. So what's the problem then? Why do people die? Especially, and you said the group that dies most often. Wrestlers. What is this going to do? You take this molecule, it's absorbed by the gut, it ends up in the bloodstream, it's very polar. Where is it going to end up?
Kidneys.
Kidneys. And so you've got all this stuff going to your kidneys. What are your kidneys going to do? Well, you got to dilute it with something. What do you dilute it with?
Water.
Water. So what does it make you do? Yeah, it dehydrates you. It makes you pee more. And so again, why does it affect wrestlers? Because wrestlers are always trying to cut weight, and part of the way they do that just before is by dehydrating themselves. So if you dehydrate yourself anyway, and then this stuff is causing you to dehydrate more, that would not be a good thing.
So for all the people that are using like the sports drink or adding this powder with creatine, they're not really doing it.
They're just making it.
They're paying a lot of money for
It's
that.
charge on
They're
that.
paying a lot of money to pee. Yes.
But he doesn't
Okay.
either.
Yeah. They're making their urine very expensive. Yeah.
Yeah. Put it in the drinks and drinking it all the time.
Yeah,
Like
they're-
$80.
Yeah. That's really expensive urine right there.
That's fossil. Oh, did I write down the wrong one?
They never believe you. You can tell them. I've had football players and stuff in
Different
biochemistry, we
residents,
talk
like,
about it,
residents.
and I talk to them later, and they're still taking all their supplements, and, you know, they will not believe you. Yeah.
See,
So it's just not even worth it, but they're not gonna believe you.